Last but definitely not least, we're looking at solving exponential and logarithmic equations. So we've already done some of this in previous sections, and today we're kind of looking at some new methods as well as compilation of all. So we're going to be talking about solving both exponential equations and logarithmic equations. So when we're talking about exponential equations, those are equations where the variable that we're solving for is in the exponent. And you're going to see two different types of exponential equations. One type, it is going to be that you can write both base or both sides in terms of the same base. So here, 16 and 8, those are both powers of 2. So 16 is 2 to the 4th power, 8 is 2 to the 3rd. So if I rewrite those as powers of 2, then I would have both sides in terms of the same base. This equation, 9 to the x equals 40. 9 and 40 are not both powers of the same number. 9 is 3 squared, but 40 isn't a power of anything. So here, I'm not going to be able to write both sides in terms of the same base, which means I'm going to have to do something else to be able to solve. So this is going to be review, and this is going to be new for us today. Okay, so let's go through these. So the first type, like I said, those that can be written in terms of the same base. So you would rewrite the equation so that both bases are the same. Once you have that, you can set the exponents equal, and then you would solve from there. So in this example, we already decided 16 is 2 to the 4th. So we have 2 to the 4th raised to the x plus 4, and 8 is 2 to the 3rd. And so we can simplify this again. If we have an exponential number raised to a power, we can multiply the powers to simplify. So this is the same thing as 2 to the, if we multiply 4 by the x plus 4, that would be 2 to the 4x plus 16 equals 2 to the 3rd. So for this to equal, since the bases are the same, our powers must be the same. So once we have the bases the same, we can set the exponents equal to each other, and then solve the resulting equation. So this equation is linear. I just have my x to the first power. So to solve, I need to isolate the x. So I'm going to subtract 16 from both sides, giving me 4x equals negative 13. Divide both sides by 4. We get x equals negative 13 fourths. So negative 13 fourths is the value of x that makes this true. And if you want, you can always verify, you can always check that if you substitute this in for x, that you do get the same value on both sides. Okay? The second type, the 9 to the x equals 40. So if we can't write both in terms of the same base, what we do instead is we either take the log or the natural log, and typically we just reserve natural log if the base of our exponent is e, and then we proceed from there. So if we take the log of both sides, we say the log of 9 to the x must equal the log of 40. Okay, so we basically assign these as the arguments of logarithms. And we can do this based on the fact that logarithmic functions are one-to-one. Okay, so moving on from here, having these logs then allows me to use my power rule, which says that if we have a logarithm where the argument is raised to a power, then we can simply rewrite it with that power pulled down as a coefficient. And so log of 9 to the x is the same as x times the log of 9. And now that we have the power, or I'm sorry, the variable out of that power, now we just have a basic linear equation to solve. So to find the value of x, I'm going to divide both sides by the log of 9, and that gives me x equals the log of 40 divided by the log of 9. This is the exact solution. If you're asked to approximate the solution, you would go ahead and figure out what the log of 40 divided by the log of 9 is. If not, you leave it. Okay? So log of 40 divided by the log of 9 gives us approximately 1.679. So this value is approximately 1.679. Okay. Next example, so we want to solve. It is an exponential equation because the variable is in the exponent. So from now on, if you're given an exponential equation, the first thing you ask yourself is, can I write both sides in terms of the same base? If you can, that's typically the easiest way to solve an exponential equation. So in this case, because I've got a base of e over here, I would need to be able to write 37 as e to a power. Because I can't do that easily, I mean, anything can be done, but, you know, for all intents and purposes, we'll say no. Okay? So therefore, we will either, if the answer to that is no, then you're going to either take the log or the natural log of both sides. And when I'm dealing with a base of e, I choose natural log over the common log for a reason you'll see in a minute. Okay, so I'm going to take the natural log of both sides, or basically assign both sides as the argument of a logarithm. So this is the natural log of e to the 2x minus 3 equals the natural log of 37. Having the left-hand side written as a logarithm allows me to take this power and pull it down as a coefficient. So rewriting the left-hand side using the power rule, I have 2x minus 3 times the natural log of e equals the natural log of 37. So now I'm going to explain to you why I chose the natural log versus the common log. And it's because of what I have right here. If you go back to what we discussed before, natural log of e, that notation ln is just shorthand for log base e. And remember, when we're dealing with a log, it represents the power we raise the base to get the argument. So what would I raise e to get e? That value would be 1. And so it's nice anytime we can get an equation and we have natural log of e, because the natural log of e is just 1. And so that's going to simplify the work that needs to be done. Okay? So this is just 1. And multiplying 2x minus 3 by 1 is just 2x minus 3. So we have 2x minus 3 equals the natural log of 37. And now I can go through, I just have a basic linear equation. I can work to isolate that x. So I'm going to add 3 to both sides. So now I have 2x equals the natural log of 37 plus 3. And then dividing both sides by 2 this is the exact value for x. To find the approximation, so in my calculator, I can find the value of the numerator. The natural log of 37 plus 3 is 6.6 da 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 da. Divide that by 2, and don't round in between, just hit divide, it'll pick up the previous answer, and that is approximately 3.305. Okay, anytime you're going to give a rounded answer, you don't want to do any rounding until the very end. So that is approximately 3.305. Okay. Alright, logarithmic equations are equations that have logs in them, okay? And we're going to be dealing with two different types. The first type is one where you can write, or you can get your equation into the form of log base A of something is equal to a number, okay? The second type are those where we can get it into the form log base A of something equals log base A of something. So anytime you're working to solve logarithmic equations, if you see logs, your first thought has to be, okay, can I get this into the form log of something equals a number, or can I get it into the form of log of something equals log of something? So here we can see this is of type 1. Here we've got lots of other stuff going on, but if we do what we did in the last section with creating or rewriting multiple terms as a single term, if we use our properties of logs, we would be able to get this equation into the form log of something equals log of something. Okay, so let's look at these two different types. So type 1, again, is an equation that can be written in the form of log base A of something equals a number, where this is any base, any number. So sometimes it's going to be necessary to use your properties of logs to get this left-hand side as a single logarithm. Okay? Sometimes it's also going to be necessary, if there are other terms or factors, to isolate those so that the logarithm is all by itself. Once you have it into this form here, then you can take it and rewrite it in exponential form, right, where it is that a to this number equals this argument. So always when it's in this form, your ultimate goal is to then get it to be rewritten in exponential form, and then you'll solve the equation that you have. Okay, so this one, log base 2 of x squared plus 11x plus 60 equals 5. So we have log of something equals a number. So it's not going to be necessary to get it as a single log because we already have that. It's not necessary to isolate the logarithm because it's already by itself. So now we can go straight into rewriting it in exponential form. So if log base 2 of this is equal to 5, this is saying that if I take 2 to the 5th power, that I will get this. So that is my exponential form. 2 to the 5th power equals x squared plus 11x plus 60. And then I solve using whatever appropriate algebraic manipulations or processes based on the type of equation we have. So 2 to the 5th, that is 32. So we can write 32 equals x squared plus 11x plus 60. So since this is a quadratic equation, an appropriate algebraic method will be to get one side equal to 0 and go from there. So I'm going to subtract my 32 from both sides. So I have 0 equals x squared plus 11x plus 28. So I can either factor or perhaps use the quadratic formula. Looking at this, I can see that it's factorable, so I'm going to go that route. So this is 0 equals x plus 7 times x plus 4, right? X times x gives me my x squared. Positive 7 times positive 4 gives me my positive 28. And positive 7x and positive 4x gives me my positive 11x. So this is the factorization of that. And so based on the factorization, then I find that my solutions are negative 7 and negative 4. And something that I don't have on here, and let's actually go back to the very first slide, and let's write it in our notes here. First slide of logarithmic equations. When you're solving logarithmic equations, you must always check for extraneous solutions. Okay? When we're working with logarithms, the argument always has to be positive. You know, regardless of what the base is and regardless of what this number is, you can't take a positive base to any number and get a negative. So in terms of checking for extraneous solutions, we have to throw out any solution that makes any argument negative. Okay? I'm not saying you can't have negative solutions. You can. You just can't have solutions that make your arguments negative. Okay? So going back to this, I got negative 7 and negative 4. So I have to check, is it okay for x to be negative 7? If I substitute negative 7 in, is it going to make this argument negative? And I'm just going to type it in my calculator and see. So if I do negative 7 quantity squared plus 11 times negative 7 plus 60, I do get a positive value, so I'm fine. And specifically, while we're at it, why not check? So if you put negative 7 in for x, this value is 32. Is it true that log base 2 of 32 is 5? Yes, it is, right? If you take 2 to the 5th power, you do get 32. So negative 7 checks out. Okay? Doing the same for negative 4. So I'm just going to go back up here, highlight this, and replace all those negative 7s with negative 4s instead of having to retype everything. And I get 32 there as well. So that checks out. Okay? So negative 7 and negative 4 are both solutions to this logarithmic equation. The second type were those, remember, where we could get log base A of something equals log base A of something. So if you can get your logarithmic equation into the form of 2 logs of the same base set equal, then this can only be true if the arguments are equal. So sometimes you're going to, again, have to use properties of logs to get single logarithms on either side. Once you have it that way, this can only be true, this log can equal this log, only if those arguments are the same. So you then set the arguments equal to each other and solve. And again, you always want to check for extraneous solutions. Alright, so we see that we've got the log on both sides. So I'm going to work to get the left-hand side to be a single logarithm. So these are both logs of base 5, which means that I can use my properties of logs since those bases are the same. Since I'm adding 2 logs of base 5, I can use my product rule that says that this expression is the same as log base 5 of x minus 7 times x plus 3. And that equals the right-hand side, which is already a single log. Okay? So for log base 5 of this to equal log base 5 of that, this can only be true if this argument is equal to this argument. So once we have our statement here, where we have a log equals a log, we can then just set the arguments equal to each other and solve from there. So this is only true if x minus 7 times x plus 3 is equal to 5x plus 15. Okay? And now I'm just going to solve this equation. So I need to FOIL on the left-hand side. So the x times x, I get x squared. Negative 7x plus 3x is minus 4x. And negative 7 times positive 3, I get negative 21. This equation is quadratic. So I'm going to get one side equal to 0. So I have x squared minus 9x minus 36 equals 0. Going down here, that is factorable. That would factor into x minus 12 times x plus 3. So that gives me x must be either 12 or negative 3. So I have to check, and remember, extraneous solutions are any solutions that make the arguments in the original equation negative. So if I substitute 12, is 12 minus 7 negative? No, so that's okay. Is 12 plus 3 negative? No. Is 5 times 12 plus 15 negative? No. So 12 is fine. What about negative 3? If I do negative 3 minus 7, is that a negative number? Yes, it is. So I can't use negative 3, right? I have to throw out any solutions that make any argument negative. It doesn't have to make all of them negative. It just has to make at least one. And I should say, actually, not just negative, but or 0. Okay? If it would make any argument equal to 0, that's not possible either. Okay, so back up here, we have the natural log of 7x minus 13 minus 8 equals negative 3. So we've got a logarithmic equation. So again, so now when you look at an equation, you first see, okay, it's a log equation. So you have to decide, can I get it to be the natural log of something equals a number, or the natural log of something equals the natural log of something? Since we've only got this one term, I see that if I add 8 to both sides, then I could have it in this form. So that's what I'm going to shoot for. Alright? So I'm going to add 8 on both sides. So I have the natural log of 7x minus 13 equals 5. And once we have natural log or log whatever of something equals a number, this type, we always then, after we get it into this form, our next step is always then to put it in exponential form. Okay? And to do that, remember, ln is shorthand for log base e. So this says log base e of 7x minus 13 equals 5, or 5 is the power that e is raised to get 7x minus 13. Or e to the 5th equals 7x minus 13. And now we just have to work to get x by itself. It's a basic linear equation, no x squared. So I'm going to add 13 to both sides. So I have e to the 5th plus 13 equals 7x. And then dividing both sides by 7. So I get x equals e to the 5th plus 13 all over 7. So that's my exact. And that is approximately, so in the numerator we have e to the 5th plus 13, and then that sum divided by 7, that's approximately 23.059. If I check it, if I multiply 7 by a little more than 23 and subtract 13, I am going to get a positive number, so this is okay. This is not extraneous. Okay? So again, here we've got this logarithmic equation. So the question is, am I going to be able to write this as log base 2 of something equals a number, or log base 2 of something equals log base 2 of something? Okay? So if you're wanting to go this route, you know, some of you might be thinking, well, I can add this over here. But the issue is this 5. Okay? So because we have this extra term, we're never going to be able to get it as log base 2 of something equals log base 2 of something. We can, however, get it into this form if on the left-hand side, because it's a minus, we can use the quotient rule to rewrite that as a single logarithm. So that's what I'm going to do. On the left-hand side, log base 2 of 9x plus 50 minus log base 2 of 2x plus 5 is the same as log base 2 of 9x plus 50 all over 2x plus 5. And now that I have log base 2 of this equals the number, once you get it into this form, you're always then ready to put it into exponential. So it must be that 2 to the 5th power is equal to this argument here. So 2 to the 5th is 9x plus 50 divided by my 2x plus 5. Again, 2 to the 5th is just 32. So we have 32 equals 9x plus 50 all over 2x plus 5. I could put the left-hand side over 1, and so now that I've got a fraction equal to a fraction, I can cross multiply to solve. So I have 32 times the quantity 2x plus 5 equals 1 times the quantity 9x plus 50, and multiplying 1 by anything just gives us what we have. So now simplifying, I need to distribute that 32, which gives me 64x plus 110 equals 9x plus 50. Is that right? 32 times, no, that's 160. Not 110. That's 160. Ignore me. Okay, and then subtracting my 9x from both sides. It's just a linear equation now. So I get 53x plus 160 equals 50. Not 53. 55. I think I need to get out my calculator. 55x plus 160 equals 50. I'm going to bring this up here. Subtracting 160 from both sides, I get 55x equals negative 110. And dividing both sides by 55, I get x equals negative 2. So checking my work, if I do 9 times negative 2 plus 50, that's positive, so that's good. If I do 2 times negative 2 plus 5, that's also positive, so that's good. So negative 2 is the solution to this logarithmic equation. So as you're going through, you need to, when solving an equation, you need to first recognize what type of equation it is, and then you need to think about your strategy and how you're going to solve. Okay? It's going to be hard if you just start doing without thinking about what you're going to do first. You need to know your strategies. Okay? So you need to know how to deal with a logarithmic equation that looks like this and how to deal with one that looks like this. And let me add to, we have to throw out any solution that makes our argument negative or 0. Okay? And then if we're dealing with exponential equations, we also have 2 different methods. Now I have to say, when you're dealing with an exponential equation, you can always use this method. So I could have solved this one by taking the log of both sides as well. It's not always advisable. Sometimes you get